So, hey everybody, and welcome to my talk. My name is Pedro, and I'm going to talk about muscle-propelled force feedback. And this is work I did with my advisor, Patrick Potash, at the Hasso Plattner Institute. So, I hope you agree with me on this one. One of the major trends in HCI nowadays is to miniaturize everything. We're trying to make devices really small and our interactions very small so that they almost disappear. And this is a couple of slides from our group. You can fill the slide with all your work as well as a community. But there are some aspects, especially on output, that have not gone through miniaturization. And the challenge that I want to talk to you today is about force feedback. And let me just break it down for you really fast and really briefly what I think is force feedback. And I'll do this at the example of a force feedback steering wheel, which is a common scenario in the 80s and 90s, if you recall, on video arcades. So we used to go and play with systems that could actually push a force on us using a motor or so. When you counteracted, when you pushed against that system, when you resisted that force, you would feel the force feedback. Now, what happens, and it's obvious just looking at this contraption here, the force feedback wheel, that the system is unfortunately not mobile at all. So instead, while you walk and you play racing games or so forth, in your smartphone, in the train or in the street, on the go, what you have is vibrotactile. And the previous talk and the others were a good example of that. Vibrotactile is very good for certain things, such as your car is driving through gravel, but it's not quite the same if your car hits a wall or something like that. So we're trying to explore that. And we find ourselves asking the question at the beginning of this project, why is force feedback that hard to make in a mobile situation or in a mobile form factor? And it turns out it's because of this. This is the canonical way of making force feedback, especially mobile and body worn. This is called an exoskeleton. It is a contraption that is pretty heavy and is made and comprised of motors and metallic rods. We call that the exoskeleton. They're heavy and they're cumbersome, and especially while you're walking and on the go, this gets into the way of your interaction. So we take a different approach, and we call it muscle-propelled force feedback. Our idea here is to create mobile force feedback devices by using electrical muscle stimulation. And particularly, we no longer have any motors or actuators, so we can make the device incredibly small and still have enough force to move the human muscles. I'll show you a video game now that actually features that. So in this video game, you're steering an airplane. When the wind kicks in, involuntarily you tilt to the right. This is the system force. Now you push against the system force, once again resisting, and this interaction, this duality of forces, is what you perceive force feedback. Alright, so as you saw on the video, and as you can see here, and bam, it's here in my hand, the device has absolutely no motors or no actuators, so it can be made increasingly small. If we put things into perspective with the exoskeleton that I showed you before, what we did was very simple. We replaced motors by our own muscles, which we drive with a little electrical current, very small and medically safe, enough to just make our muscles contract. We no longer need the exoskeleton, the metallic rod, and we don't need a big battery pack. We just need your body energy and a little current that is so little that actually we can discard it, basically. So our contribution is to create a way of getting force feedback on the go using electrical muscle stimulation, which is something that we did not invent. Researchers in the 60s started playing around with this concept for rehabilitation purposes, sore muscles, and so forth. It found its way into HCI, into simulations such as virtual reality to render haptic stimuli, and also 2 years at Kai, Rekimoto showed how it can be very useful in learning tasks to mediate your input, like when you're learning a new instrument, here the koto. But we focus on this duality of forces and on deriving a very, very, very small form factor. So let me talk a bit about the form factor and how we actually made it mobile. So I'll invite you to look at the device and imagine that it's kind of slid on your mobile phone. So we'll see it from this perspective. So the first thing we have is the phone, and we use the accelerometer. This is important. We use accelerometers to get like an encoder, so we know how much you actually tilted or contracted. Then we use wireless communications. Through a Bluetooth modem, we control the whole thing using an Arduino Nano microcontroller, and this is the kicker. The Arduino is actually controlling a signal generator that basically sends the waveform, kind of like your nervous system uses to communicate and tell your muscles to contract. Now, once that waveform is amplified using medical compliant amplifiers and sent through the electrodes, your muscle actually contracts. So we were interested to see if this contraction was comparable with existing force feedback devices. So, user studies. And the first one, we asked ourselves the question, are we driving here enough force? Are we outputting enough force? So we set down participants, and this is close up here, it's over there, and we strapped them down to the palm flexor, electrodes here on this muscle group. We measured the peak force with a spring scale, and we calibrated the prototype per participant through a barely minimum visible motion to instill a level that it was completely pain-free for everybody. So this is what we get. There's a linear relationship between the time that you let the intensity go through your muscle and the force that's being generated. Now what's interesting, at a minimum, everybody produced at least 50 newtons of force. On an average, everybody produced enough force to lift a 2-liter water bottle just with the wrist itself. Over 400 milliseconds, and I think this is interesting for the haptics community, we have 3.3 newtons, comparable to the phantom force vector device, which is kind of the canonical thing we have in our labs to make force feedback. So, more interesting, we were hoping to get some excitement with other people, so that's what we did next. We made them play the video game that you just saw, the airplane steering, under 2 conditions, muscle-propelled force feedback and vibrotactile. And for the vibrotactile, what we did is render the wind coming from the left as a continuous buzz, zzz, and the one from the right as a rhythmic impulse, zzz, zzz. And they were trained to recognize this. So, and we got really good results. They all preferred force feedback over vibrotactile, and we got a lot of comments that suggest an incremental sense of immersion. But I acknowledge there's a novelty effect here. We just showed people some new device, obviously they get excited. So instead of this, I want to also show you some feedback that we got here at Kai over this last 2 days, showing our demo. So I hope you recognize some of the faces. We're really excited because people seem to have a lot of fun with this, especially playing the game. So, I also want to talk about the limitations of this approach. One of the things, and if you try their demo, I was the one that did this to you, you have to manually place the whole thing in one-time calibration. Secondly, accessing the body here in a controlled experiment is pretty easy, but in a broader scale, it might be unfamiliar to some. Future form factors, because there's no motor actuators, we can make this thing so small that we can make bracelets out of it, or even in the future, maybe even implant it. So as a conclusion, we talked here about how to make force feedback mobile, and we did it using electrical muscle stimulation. I just want to show you one more clip while I say something to you as a takeaway message. What I think is really interesting here is this work kind of focus on the duality of HCI. HCI typically is about machines, humans controlling machines. There's a role inversion here, and people are being controlled slightly by the machine. So what I also think caused so much excitement on people while we're experimenting with this is how in the future will devices actually interact with us, and how will they output new modalities and so forth. So I hope you take this message home and visit our booth.
Ken Perl in NYU. This is really wonderful work.